So today I'm going to be talking about Chapter 22. This video will cover Section 1 of Chapter 22. So we are going to be talking about the zero age main sequence. What does that phrase even mean? And what happens as stars begin to run out of fusion and start moving off the main sequence. So zero age main sequence, we have been looking at stars as they are contracting and getting smaller as they move left on the HR diagram, but not doing fusion yet. So the point where they begin to fuse hydrogen into helium is where we find ourselves on this red line. So that is the zero age. And we notice that the line for the zero age main sequence matches the main sequence. It's basically the leftern edge of the main sequence. And so we will find stars all on this region for the period of their life. And so what's happening is that we have hydrogen burning in the core, and then the outer core, all of those outer layers of the star. In this case, we call it the star envelope, but it's all the outer layers. And in these outer layers, it's not hot enough for fusion. We talked about that when we talked about the layers of the star. For a star the size of our sun, the core is around 15 million Kelvin, and it cools off through all of this. So this is not the scale. When the star just begins to run out of hydrogen, we have the helium that is settling into the core. Remember differentiation, and as the heavier particles settle into the center of a planet, the same thing is happening in the star, and helium is minutely heavier than hydrogen, so it settles into the center. And so we have a helium core that's just sitting there, and hydrogen burning in a shell around the outside. Once again, not to scale. So helium fusion is different than hydrogen fusion. For hydrogen, what we looked at previously was the proton-proton chain. Two hydrogens fuse, two deuteriums fuse. So helium's different. We have to have three heliums to create a hydrogen, and once again, energy is left off, or created. It's not even created. Created is a bad word for this, but energy is released. There we go. So because the helium have a greater charge than hydrogen, they also have a greater repulsion, and so you have to get to much higher temperatures in order for this process to occur. And so helium, as the star begins to run out of hydrogen, the thermostat, that equilibrium that allowed it to, just sit there and slightly pulse, the thermostat's broken, and degeneracy pressure is what's supporting the core. The molecules, the helium in the core are saying, no, I don't want to talk to you. And we have lots of pressure, and so the core temperature rises, and we end up with what we call the helium flash. Helium fusion, begins and skyrockets, really quickly, so that thermal pressure takes over because there's now extra energy being released in the core and expands the core again. So as we, have a one solar mass star, We notice that it will not leave the main sequence until it's a billion years old. Compare that to a 15 solar mass star, the age of this is similar to Betelgeuse, and so it leaves the main sequence 1.01 times 10 to the 7. So let's remember, what is that? 1 and 7 spaces over here. So we're talking about, a million years instead of a billion. But the bigger a star is, the faster it lives its life. We're going to see this repeated several times. And so based on the age or the size of the star, we can see the age that it will live to and where it tracks. Stars like ours become red giants. Stars like Betelgeuse become hypergiants. So the radius is increasing, luminosity decreasing. And so that is basically the zero age main sequence. And I will do another video that will talk about section 2 of chapter 22, and we're going to talk about star clusters, why they're important, and how they help us figure out the ages of stars.